Hello everyone. Today we're going to start a new case study, the CPU Meltdown exploit in 2018. So the first parts are some standard disclaimers. The company involved in the cyber breach hasn't publicly released all the detail of the incidents and probably will never do so, but enough information exists online and within the cybersecurity community to piece together what likely happened during the breach. Although care has been taken to ensure accuracy of the information provided, the presenter assumes no responsibility. Therefore, the presenter also assumes the responsibility for consequence of using such information. So this case study was adapted from the CPU Meltdown exploit in 2018, and information was taken from many public sources and modified for educational purposes. I also list some additional resources you can take a look at the end of this PowerPoint. So a little bit background. So the CPU Meltdown exploit was independently discovered and reported by 3 teams in June 2017. Okay, the first team come from Google. Okay, the second team come from a smaller company. The third team, I believe, come from a university in Israel. Okay, and the Meltdown, basically they take advantage of a CPU design flaw. Okay, and it allows any program to read sensitive information in the memory and with unprivileged access right, and they can read arbitrary memory including some kernel memory. Okay, another similar name, it's called Spectre exploit. However, it's slightly more complicated, so we won't cover it here. Okay, so this is just very basic introduction. I'll explain more here. But before that, let's just briefly talk about the side channel attack. Okay, the modern CPU has been very carefully designed and manufactured. So if you want to launch direct attack on modern CPU, your chance of being successful are very slim. And that's the reason why people start launching all kinds of side channel attack. Okay, what exactly is side channel attack? Is actually a very common type of attack. So basically attack that derive information from non-direct or unintentional information source. Okay, give you some example. You can get information from sound, from vibration, from electromagnetics emissions. Okay, give you some example. The first one is acoustic cryptanalysis. Okay, so basically, for example, the sound of key clicking can be analyzed and a typed face and the password can be recorded. So if you have some kind of a camera or smartphone, you can record people's key clicking. Okay, you'll be able to recover password. Now, supersonic sound directed at the accelerometer can alter the reading or ultrasound to attack serial. Okay, all this attack I listed here are not just are actually paper published in cybersecurity conference. Okay, so those are real attack. Researchers have found out those are possible attack and they show the demo. Okay, so there's a number of this type of attacks. Okay, another type of attack is called another example is electromagnetic emission. So we know like CRT monitor generate a lot of emissions, and if you collect those emissions and use those information to reconstruct information, and you'll be able to actually guess what's displayed on the original screen. Okay, again, all those attack scenarios are actually published work. Okay, so these are just some example of side channel attack. basically you can see they basically, instead of directly attacking your device, they kind of collect information from side channel and try to derive sensitive information from those side channel. And because when people start designing their system, they don't expect people to derive information from those side channel. So they put very little protection on those side channel. And that's the reason why side channel attack nowadays are very popular. Okay, so the CPU meltdown is one example of side channel attack. Now let me give you some background information about the CPUs. So the modern computer, including the CPU and the operating system, try to ensure that a user program cannot randomly access other people's data or other people's memory without authorization and authentication, which is a normal thing they should do. And the modern CPU has built-in security mechanics to support that, and it worked very well. Okay, and until the meltdown. Okay, the modern CPU have internal cache, and the purpose is to speed up the memory access, so it's much faster than the main PC RAM. Okay, and another thing in modern CPU, they are using out-of-order execution to speed up performance. Okay, let me explain a little bit about out-of-order execution. So instead of just waiting there for the execution, modern processors run operation out of order. So they look ahead and schedule subsequent operation to idle execution units of the process. So think about this. So this CPU can do many things at the same time. Okay, they have many processing units, and some of the units probably have to wait for the result from the other units in order to continue execute. Okay, and that's actually a waste of resources. So what they do is they actually speculate about the result and keep running. In that way, you don't have to wait. And of course, there's a chance your speculation is wrong. Then the result will be discarded. But if you design the algorithm carefully, those out-of-order speculation actually have very high successful rate. Then you really speed up the performance. So this is a very common technique in modern CPU. And this is called speculative execution. So the CPU guess what outcome of the execution would be, and then execute subsequent steps in the background. And the CPU cache memory store the data, and the CPU copy information from main memory and store it in the cache. The main memory is where you put all the data. Okay, and the CPU will protect the memory from being read. And the protection is not honored during the speculative execution. Now this is causing some of the issue. And the CPU speculate and execute. If correct speculation branches, then store in the cache. So basically this is how the modern CPU works. It may look a little bit complicated, but it works really well until the meltdown. Okay, so the software try to compare protected memory item to the some other things. If it return true, it will be in the CPU memory and return fast. If it's not, then it will return from the main memory and run slow. Then if you just track the result image timing, okay, if the timing is fast, that means it's true. If the timing is slow, that means it's false. Okay, so this it's really just utilize the timing difference between CPU cache and the main memory. And that's the side channel attack. Let me explain a little bit about the technical details of Meltdown. So security is based on separating kernel memory address range that are not accessible by the user space. So Meltdown allows non-privileged user to read kernel memory. And Meltdown take advantage of out-of-order execution, which also called speculative execution. So the first thing, the malicious software will clean up the cache memory. Okay, it just avoid any interference. Then the malicious software make a request to read the kernel memory, which is illegal because it's protected. So the malicious software make a second request and conditionally read a valid memory location and trying to see if the first request contain a certain value. Okay, that's allowable. And with speculative execution, both requests are executed before both requests are denied because of illegal out-of-bound memory. However, because both requests are denied, results are not returned. However, because of this speculative execution, both requests were processed and accessed memory location are stored in the cache memory. Okay, I'm not sure if you really follow me on this, but let me give you a metaphor or analog by using McDonald's. Okay, hopefully this will help you to understand what happens. Okay, so McDonald's has food such as fries or Coke or hamburger. Let's just name three, make things simple. So assuming Taylor Swift, I know this is a famous singer, I'm not a big fan, but let's just use her as example. Okay, she went to McDonald's, which unlikely, and ordered a hamburger and left. Okay, so now you know she's a famous singer, so pop star. So there's a lot of paparazzi guys behind Taylor Swift, and told the McDonald's people, I want to order the same food as that pretty lady. Now, of course, McDonald's people will say, please wait in order. There's one person before you. But during this process, the people in McDonald's kitchen overheard of the order. And to speed up the process, he speculated and made a hamburger and put it on the shelf. This won't happen in McDonald's, but it will happen in the CPU. Remember, this is called speculative execution or out-of-order execution, just to speed up. Now, it's A's turn to order, okay? But the McDonald's front desk says, you cannot order like that. It's a violation of privacy. Now, of course, it's a violation. So, A is kicked out of McDonald's, okay? Now, another paparazzi guy, B, it's behind A. So B said, give me an order of fry or Coke or hamburger. I'm starving. Whichever fattest, please give it to me. Okay? Now, B is actually using a little bit smarter way, whichever fattest, give it to me. And because in the back kitchen, we already have a hamburger there. So B actually get a hamburger. Okay? Now, the paparazzi guy B will know Miss Taylor Swift ordered a hamburger at McDonald's. Okay? Now, of course, here is a hidden assumption. The paparazzi team need to make sure McDonald's shelf is empty at the very beginning. And that's the reason why you need to clear the cache in the CPU. Okay? I hope this analog really helps you to understand how things works in the CPU meltdown. Let's do a more technical example to explain things. Okay, so suppose the address at 3000 is not directly readable, and it could have any value from 1 to 5. A hacker could execute its instruction read memory at address given by 5000 plus the value of memory at address 3000. Okay? If address 3000 contains 1, the CPU will try to return the value of 5001. and if the address contains 2, it will be 5002 and so on. So if the hacker execute a timing attack and show that CPU was slower to read from any of those addresses but faster from 504, then the hacker can conclude it's probably you read things from cache, okay, for 504. Then it's become recently accessed, so you can just deduce that address 3000 may contain the value 4. Okay, I hope combine these two analog together, it helps you to understand the meltdown. Okay, so the impact, basically all the Intel processor having this issue because out of order execution are very commonly used. Some of the ARM processor are also affected, and almost all the desktop, laptop, phone embedded system, especially the servers, cloud servers, that causing a lot of issues. Okay, so basically you can read arbitrary real memory address space. Okay, it will allow unprivileged account access to sensitive data. Okay, and especially when you are using virtualization or you are using cloud computing, usually you want to do isolation, but this can be compromised. So allowing a virtual guest to read other people's data, okay, and that causing significant concerns. Solutions. The solutions are simple. Basically, you have some software updates to help mitigate the risk of this type of memory cache side channel attack. However, it comes with a performance penalty because you just doesn't allow out of order execution. And there are also hardware issues, okay, and can only be truly fixed by replacing the hardware, which is very costly and difficult. So the real fix is really for Intel to redesign the CPU architecture. The lesson we learned, Meltdown explored CPU cache side channel attack to read protected kernel memory. And basically this is some kind of privilege escalation and provide a dump of physical memories. Virtualization, cloud computing are very vulnerable. Basically guests can read the host shared memory. Okay. Now here, this CPU meltdown, it's actually just the beginning. Okay, after this, more and more similar CPU or chip-related hardware exploit using side channel attack are discovered by the researcher. Because in the past, people never think this would be possible. But once the first type of attack is possible, then people start looking all kinds of this type of CPU side channel attack, and it's a very hot research area. So here I list several articles about the newer development after the original meltdown. So for those who are interested, you can take a look. Here I have shown you some resources. The first one is a wiki page, basically give you some basic information. And here is a short YouTube video explaining what is CPU meltdown. And resource 4 is a much longer video explaining. And here is actually a technical paper. Okay, if you go to download this technical paper, you're actually getting a lot more detailed information. This is actually the paper they published, original author published. So now here is the paper, the meltdown paper I mentioned. Okay, this one is giving you very detailed information about how these things happens. And again, if you take a look at this chart, there are a lot more detailed information here. So I'm going to just show you some of the things. So here, look at this diagram here. Okay, so excuse me. this diagram here shows you the difference of access time. Okay, so you can see normally the access time, for example, is like 400 at this level here. That's the normal access time. And here, because it reads things from the CPU cache, you can see a significant dip, a much faster access. And here the reading is probably like 200. So the normal thing is like 400-500. With the cache, it's like 200. So if you can timing these things, you'll be able to launch this type of side channel attack. Okay. Again, I'm not going to go through this paper, but this is something you can take a look, and it's a very useful paper. Okay, help you to understand Meltdown. Okay, thanks.